Uh, my name is Takumi Nakayama. I'm a master student from the Tokyo University of Science. Today I'm going to present my studies. The title is The Prediction of Future Heat Stress in Japan and the Influence of Individual Meteorological Elements of Future WBGT. Start from the background. Uh, Nowadays, temperatures are rising on a global scale, and because of that, the heat mortality rate is also increasing. Evaluating future heat stress is very important to make countermeasures for the serious stress. For example, there is a countermeasures for the heat stroke in Japan, which is called the heat stroke alert. It is issued in prefectures where WBGT is expected to be 33 degrees or higher. There are more uh, while there are many existing studies dealing with future and current heat stress by using simulation, most of them are uh, based on the uniform urban parameter. So it is difficult to say that they adequately reproduce the urban heat stress. So in my study, I have a two approach to evaluate future heat stress. One is that using the large number of data and clarify the changes in the number of days that heat stroke alert will be predicted. The other one is that evaluate using the high resolution data and evaluate the current future heat stress using WBGT by incorporating realistic urban geometric parameters and reveal the effect of individual weather elements on future changes in WBGT. This is the date set that I used for the heat stroke alert prediction. And the U4 PDF is a date set that provides the result of global and regional numerical experiments. They has a large number of ensemble data. They has several scenarios and ensemble members like below, like here. And I choose the 2 Kelvin running scenario and the 4 Kelvin running scenario and 12 ensemble members respectively. To make data high resolution, I use the I use this method called the self-warming method. Let me explain how to uh, make an initial boundary condition. Firstly, make the future and present climate values by averaging 10 years of data. Then add the difference between future and present climate values to the objective analysis data. The weather weather element that I consider were temperature, wind speed, and geopotential altitude. There are some advantages of using this method. The first one is that you can get high resolution data by using dynamically downscaling, so you can evaluate heat stress accurately. The other one is that you can eliminate the model's bias by uh, using the difference from the data. This is the simulation setting. I set the first domain and the second domain like right figure. And for the present simulation, I use the EAR5 for initial and boundary condition. For the future simulation, I use the D4 PDF for the making the climate values and EAR5 as the objective analysis data. And also I choose the 2 Kelvin and 4 Kelvin running scenario and ensemble for ensemble. This is the thermal comfort index that I used, which is the WVGT. You can get outside WVGT by calculating by following this formula. The burning globe temperature is affected by the air temperature, radiation, and wind speed. Wet bulb temperature is related with these three, and water vapor pressure. The WBGT stress categories are following this graph. However, you cannot get Varangium temperature and wet bulb temperature directly from the simulation output, so I calculate each temperature by using the heat balance formula. This, this is a result of the future changes in heat stroke allowed prediction. These results were averaged 12 ensemble data for each cases. The range shows the future changes in times that the future uh, the heat stroke alert prediction heat stroke alert is predicted. From the left graph, you see that there are just a few changes. On the other hand, for the 4 Kelvin warning scenario, you see that there are large changes, especially the lower latitude. Um, let's look at more detail. I focus on the Kanto region because that is the most dense area in Japan. This is a result of a dynamically downscale WBGT into 1 kilometer at noon in August. Uh, this is a pleasant and 2 Kelvin warning scenario, a 4 Kelvin warning scenario from left to right. The ranges shows the ranges follow the WBGT stress category, like here. From the left graph, you see that the WBGT exceeds 33 degrees in Otemachi, downtown Tokyo, and around Kumagaya, one of the hottest city. From the middle graph, you see that the area up above 33 degrees were expanding. From the right graph, you see that almost all area uh, were exceed 33 degrees, except the coastal region. Then let's check the which bulb temperature has the most impact on WBGT increase. This is a contribution rates of the each bulb temperature in Otemachi, downtown Tokyo, and red color and yellow color represent the 4 Kelvin and 2 Kelvin warning scenario, respectively. The final contribution rates is the future changes of each bulb temperature divided by future changes of WBGT. Under 2 Kelvin warning scenario, the contribution rates were larger for the burn-on globe temperature, wet bulb temperature, dry bulb temperature in the order. In under 4 Kelvin warning scenario, the contribution rates were larger for wet bulb temperature, burn-on globe temperature, dry bulb temperature in the order. From this result, we could say that the effect of uh, humidity or the radiation or air temperature could be high because the contribution rate of these two were high. Then let's look at more detail and check the which weather elements have the largest impact on the future WBGT increase. This is due to the time I just introduced the 2 Kelvin warning result of 2 Kelvin warning scenario. This is a result of sensitivity analysis in Otemachi and Kumagaya. The vertical axis shows the the weather elements, and these green lines shows the effect of each weather element. From this graphic, uh, in automagy, the, the radiation was the largest impact on future WBGT increase. In Kumagaya, temperature was the largest impact on the future WBGT increase. The summary. This is a summary. Thank you for listening.
Thank you. I don't want to add a future event.